Hey everyone. We were supposed to cover section 4.1b, the second derivative test. This is actually a really short section, so this won't take very long. The idea of the second derivative test is to be a shortcut to the first derivative test. Excuse me, which is what you did in 3.4b on the last test. Okay, so shortcut to that. So here's what we're going to do. We're going to find critical values the same way we did in section 3.4. You do that by taking the derivative, setting equals 0, and solving for x. Once you have that critical value, we'll take it and plug it into the second derivative. Okay, I'm going to use the letter C here for critical value. One of three things can happen. Either you can get a positive number, a negative number, or it could actually equal 0. Of course, 0 is neither positive or negative. What's going to happen is this. If we get a positive number, we learned in 4.1a last Tuesday, that you would have something called concave up. Concave up looks, like that, like an upward parabola, like a U shape, basically, without the tail. So if you have that sort of shape, there's a low point on it right here. It's below its surroundings, so you have a local min in that case. So this is concave up, so we have a local min. So anytime the second derivative gives us a positive value for that critical value, then we have a local min at that critical value, comma, the y value that you'd have to calculate. Plug into the original function to get your y value. If the second derivative comes out to be negative, that would be concave down. So that's just basically flipped over. Okay, if you have that situation, I'm sorry, then you have a local max. Okay, so basically a high point on it. So then local max at C, comma, f of c. Okay. The one bad thing about this shortcut is occasionally the critical value will end up showing up as equaling 0, which again, 0 is neither positive or negative. When that happens, you can't tell if you have a max, a min, or neither one. So you'd have to go back and do the first derivative test anyway. Again, we did that in section 3.4b. That was on the last test. Okay. So there it is. There's our second derivative test. Okay. All right, so let's look at a problem. Let's say we're looking at this problem. This is straight from Hawks. Use the second derivative test to find all local extrema if the test applies. Otherwise, use the first derivative test. So when they say if the test applies there, what they're literally saying is if you have a situation where it's this third case where it actually equals 0, you'd have to go back and do first derivative test. I'll go ahead and give you a hint. None of them should work out like that. Okay? You're all going to see either case 1 or case 2 here. So let's take this problem. f of x equal 2x squared plus 16x plus 30. Okay. We need the critical values. Okay, so you get that from the derivative. So take the derivative, that'll be 4x plus 16. Set it equals 0. Solve for x. (16) divided by -4 is going to be -4. And you can plug that in the original function and you'd have you would have a critical value there. In fact, why don't we go ahead and do that. So y is going to be f of -4. So 2 times -4 squared plus 16 times -4 plus 30. So -4 squared is 16 times 2 is 32. 16 times -4 will be -64 plus 30. That'll be, 62 minus 64 is going to end up being -2. So you found a point -4, -2. Alright, so that point is going to be a max or a min. We just have to figure out which. So again, look back at our rules here. Once we have the critical value, we take it and we plug into the second derivative, and we're either going to get greater than 0 or less than 0. Depending on what we get there, we'll have a local min or a local max. Okay, so let's get our second derivative. The derivative of 4x plus 16 is 4. Okay, if we plug our critical value in, we're still going to get 4 for the second derivative. In other words, that's a positive number. We said if we have a positive number, that's the first case here. So we have a local minimum at c comma f of c. Okay, so for us, we have a local min at this point we found. That was the only point we have, so no local max. Okay. Now alternately, you could go back and do this problem the way you did in 3.4b with the first derivative test. That's where you found the critical value and you put it on a sign chart. You plugged in test values into each interval and got, the increasing, decreasing signs on the sign chart, and determine local min or max from that. But again, this is supposed to be a shortcut, so it doesn't really matter to me. If you still want to do it the way you did in 3.4b, that's fine. This is just supposed to be a little bit quicker. Okay? So let's put that answer in. Again, no local max, and local min was -4, comma, -2. And let's go ahead and submit. Alright, there it is. Okay. Let's take another one. That one will work. You'll notice some of these, they have it broken into 2 steps. With the first step, they're just asking for the second derivative. So, I mean, we can do that. You've got to get the derivative anyway. So it's not going to hurt to go ahead and do it up front. Let me write my problem down here. Okay. -2x cubed minus 3x squared plus 12x plus 12. Alright, first derivative, -6x squared minus 6x plus 12. Set it equals 0. Solve for x. I can pull a -6 out of this. That's going to give me x squared plus x, minus 2. So let's see, that's going to be x plus 2 times x minus 1. Alright, so if you solve this, you'd have negative 6 equals 0, x plus 2 equals 0, x minus 1 equals 0. So you're going to get x equal negative 2 and positive 1. Okay, you're not going to get anything from this. Alright, so you actually have two critical values this time. We'll use those in a minute. Go ahead and get the second derivative here. So again, I'm looking at the first derivative and taking the derivative of that. So the derivative of negative 6x squared will be negative 12x, and the derivative of negative 6x will be negative 6. The derivative of 12 is 0. Okay, so that's all they're asking on step 1 here is the second derivative. Negative 12x minus 6. Oops. Okay. And then part B, local max and min. Okay, so let's go back over here. We've got these critical values. We need to check them to see what they are. So plug them into the second derivative to determine max or min. So if I plug negative 2 in the second derivative, negative 12 times negative 2 is 24, minus 6 is going to be 18. That's going to be a local max. Excuse me, a local min, I should say. Negative 2, comma, some y value which we'll need to calculate. If I test the other y value here, f double prime of 1, negative 12 times 1 minus 6 is going to be negative 12 minus 6, which is negative 18. That's less than 0, so that's a local max. 1 comma, again, some y value that we'll calculate. Alright, so you've basically got it. You just got to get your y values now. Okay, so let's go back up here. If we plug negative 2 into the original, negative 2 times negative 2 cubed minus 3 times negative 2 squared plus 12 times negative 2 plus 12. Let's see, negative 2 cubed is negative 8 times negative 2 is 16. Negative 2 squared is 4 times negative 3 is negative 12. 12 times negative 2 is negative 24. Now we still have that plus 12. So let's add that up. Negative 12 plus 12 is gone. 16 minus 24, you're going to have negative 8. So that was when we plugged in negative 2. So that's our y value there. Oh, I'm sorry. Alright, we still need a y value for when x is 1. Okay, so plug 1 into the original function. So this would be negative 2 minus 3 plus 12 plus 12. So what's that? 24 minus 3 is 21, minus 2 is going to be 19. Okay, so there we go. Again, same process. The only difference was we had two critical values this time, so we had to check both of them. So you've got a local min at negative 2 comma negative 8 and a local max at 1 comma 19. Local min was negative 2 comma negative 8. Okay, there we go. Alright, these all pretty much work the same from here on. I want to go over and get the actually the ugliest problem. Actually, let's go ahead and do this. This will be fun. Alright, so x squared plus 9 all squared. So the first thing they want is the second derivative. My suggestion, since this is only squared, go ahead and multiply it out so you can just deal with the power rule. If you leave it in this form, you're going to have to deal with the chain rule or the general power rule. But if you multiply it out, you can avoid all that. So let's go through and get our second derivatives first. Okay, so that's again same as x squared plus 9 times x squared plus 9, which is x to the fourth plus 9x squared plus 9x squared, so plus 18x squared plus 9 and 9 is 18. Okay, so we just multiplied it out, FOILed it out if you want to call it that. Alright, now let's go through and get derivatives. So first derivative, 4x cubed plus 36x. Derivative of 18 is 0, so that's gone. While I've got the first derivative there, let's go ahead and get our critical values. Set your derivative equals 0 and solve for x here. Okay, so we can pull a 4x out. So 0 equal 4x, 0 equal x squared plus 9. So we're going to have x equals 0 from that one. That's critical. This one, let's see, let's move the x squared over, divide through by a negative. Okay. Have an issue here. When we take the square root of both sides of an equation, remember in algebra, well, first thing you're supposed to do plus or minus. Okay. But the second thing is we're trying to take the square root of negative 9 right here. Okay. We only deal with real numbers. Okay, so you actually can't do that. Okay. So we're not going to get anything from this. That's fine. That just means you have the one critical value, 0. Okay, keep going. Our second derivative. Again, I'm going to go back up here and look at my first derivative. Do the derivative of it. So this will be 12x squared plus 36. Okay, so question asks for second derivative, 12x squared plus 36. Okay, and then local min and max. Okay. Alright, so we plug our critical value into the second derivative. If you do that, you're going to get 36, which is positive. So you have a local min again. That's going to be 0 comma something. Okay. All that's left is to get your y value. So I'm going to go back to the original function and plug in my critical value. So that'll be 0 squared plus 9 all squared, which is just going to be 9 squared, which is going to be 81. Okay, so we have a local min there. We don't have any local maxes. This one looks almost the same, but there is going to be a slight difference to it, so I'm going to go ahead and do it, and then that'll be everything. So 3x squared minus 3 all squared. And same idea, I see this is squared. I'm going to go ahead and multiply it out. Alright, so multiplying out, that's going to be 9x to the 4th minus 9x squared minus another 9x squared, so minus 18x squared plus 9. Your first derivative, 36x cubed minus 36x. Set it equals 0. Solve for x. Okay. X squared minus 1 actually factors this time. Give me 1 second. Okay, sorry about that. My kids got home. Alright, so let's set these all equal 0. So x is 0, x is negative 1, x is positive 1. Alright, and those are all critical. They can all be plugged in up here and a value calculated. So you're going to have to do 3 of them this time, which is not really a big deal, but that's what we have to do. Okay, question asks for the second derivative. So let's go ahead and look back at our first derivative again. Get our second derivative. 36 times 3 will be 108. It'll be x squared minus 36. Alright, so let's plug that in. 108x squared minus 36. Correct. And the final part, the local extrema, local max and min. Okay, so let's plug in our different critical values. If I plug in 0 here, I'm going to get negative 36. So that's a local max. If I plug in negative 1, I'm going to have 108 minus 36, which is, 72. So that's a local min. And if we plug in positive 1, we're also going to get 72, which is a local min. Okay. All we need now is our y values. Okay. So if we went back to the original there and plugged in 0, we'd have 3 times 0 squared minus 3 squared, which is going to be 9. So this will be 0, 9. If we plugged in negative 1, 3 times negative 1 squared minus 3 all squared. Negative 1 squared will be 1, times 3 is 3, 3 minus 3 is 0. 0 squared is going to be 0. So it's going to be negative 1, 0. And lastly, if we plugged in positive 1, we're going to get the same thing. Okay, so that's going to be 1, 0. Alright, so you have 2 local mins this time. I'm sorry, I didn't show you the screen here. So we took our second derivative of the first derivative to get our second derivative. Plugged in each of our critical values to determine local max or min. Okay, so this one was negative, so it was a max. These two came out positive, so they're mins. All we needed at that point was our y values, so we went back and plugged our y values into the original function, and calculated the y values. So if I plug in 0 in the original, I have 9. I plug in -1 in the original, I have 0. Plug in +1 in the original, I have 0. So those are our points. So if you have 2 points that are both the same type of extrema, just separate them with a comma when you put them in Hawks. So let's see, a local max of 0,9 and local mins were -1, 0 and +1, 0. So again, just see, I'm just separating them with a comma there. It doesn't matter what order you write them in. Okay, and there it is. So that's probably the toughest one on here. You'll notice we didn't give you any product rule or quotient rule or anything like that. So just for simplicity. Okay, I will see you in class on Thursday.